Oh, hello, everyone. It's time for us to start the session. Please have a seat. Does anyone know how to turn light down a little bit? Maybe not. Okay. So welcome everyone to the Rubin Community Workshop 2025 and the introduction to Rubin session. I am Yumi Choi. I'm chairing the session and I'm an assistant astronomer at NOAA Lab and a member of Rubin Community Science Team, CST in short. And Christina Williams, another CST member, will monitor Slack and Zoom during the session. And here is our Slack channel for the session. Oh, okay. And we've got a bunch of super useful talks lined up for the session. And before passing the floor to the first presentation, I will go over some important and useful information about the workshop. So first, reminder about the code of conduct. So harassment and unprofessional behaviors are not permitted during the session, the workshop. So if you experience or witness any violations, please reach out to one of these people. And then the full code of conduct is available on the website, workshop website, or via this QR code. And if you have any COVID-related questions, please use this confidential email. Oh, by the way, all the slides are linked on the session website, so you don't need to jot down all the information. And then wearing a mask is completely up to you. And if you see any types of these stickers on people's name tag, then please check their contact comfort level and respect others' choices. For lost and found, please use the RCW registration deck, not the hotel. And if people wearing this cool-looking pin and indicating a low social battery, then please give them some space. In short, Rubin Observatory emphasizes a respectful, professional, and supportive environment. Okay, second reminder about the virtual participations. So this workshop is fully hybrid. For the virtual participants, please mute when not speaking. And in-person participants, please use the speak to the room microphone so everyone can hear you, including those online. And then the Slack is a great place to post your questions and to keep the conversation going. So you can post the question there. And in Zoom, please request to unmute or type your question so our moderator can read aloud. Okay, and here's a list of key activities about the workshop. So if you're new to Rubin or you need looking for a refresher on all aspects of Rubin Observatory, this is the right place, right session to come. And all sessions are open to all attendees, everyone. And every morning we have plenaries from 9 to 10 a.m. And after that, we have 3 parallel breakout sessions, start 9:30, 10:30, 1:30, and 3:30. Monday through Thursday, and Friday we'll have only morning sessions. And Tuesday we'll take a group photo at 5 p.m. in the lobby. Wear your Rubin shirts if you want to. And reception is also on Tuesday at 6 p.m. at Gentleman's. And here are the list of breakout sessions with broader impact. So if you're new to Rubin, these are the cool things to check them out. And on Wednesday, 3:30 p.m., there is an on-conference session. So suggest a topic on the board and then vote for the ones you like. And on Wednesday, the rooms and topics will be assigned. So just come to the ones you're interested in. And there are 2 poster sessions, 2 sets. So the first set will be up all day, Monday and Tuesday, and the second set will be up on Wednesday and Thursday. And then the poster presenters will be stand by their posters on today's and the Wednesday afternoon break. Rubin Research Bites, RRBs, is an informal and informal way to share your Rubin-related work at any level. So please consider to contribute one for fun, and please visit this page for instructions to post. All right, so this is the agenda again, and I think I used up my 5 minutes or so I will give the floor to the first speaker, Tiago Ribeiro, will be talking about telescope insight.
Hello, everybody. I'm going to be talking about the Telescope Insight group and Rubin Observatory. I think this is probably the last time I'm going to talk about Telescope Insight, because this is a construction team, and in operations we become observatory operations. The Telescope Insight team was responsible for the construction of the telescope, of the observatory, and the base facility. So that includes a really diverse set of things. Like we were in charge of constructing the civil work to build the telescope, the observatory, both the Simony telescope, the enclosure, the coating chamber, all that was in Telescope Insight, and the auxiliary telescope as well. So the civil work required to build this amazing machine was Telescope Insight, but we were also in charge of building the software to control the observatory. So you can imagine a team like that requires a really diverse group of people to work together. So from engineers, electronic teams, software engineers, and test engineers, and scientists as well. So I have some jargons and nomenclature here to share with you. So the Simony Survey Telescope and Auxiliary Telescope were both part of Telescope Insight construction. The TMA, the Telescope Mount Assembly, is the telescope itself. We have the dome. The dome includes the enclosure, the light screen, the shutter, the vents, the M1 and 3, and the glass, the primary and tertiary mirror, the secondary mirror. We have the camera hexapod, the rotator, and then beyond that, the hardware part, we have the software. So the observatory control software, something that we talk a lot about is the service abstraction layer, SAL. So if you are ever interacting with the observatory control software, you see us talking about this SAL, which is how the components talk to each other. This is an abstraction that we created to facilitate developing the components. So the communication channel is abstracted. So when you are writing a software component in the control system, you write, on top of this framework. The EFD, the Engineering Facility Database, it stores all the communication. So every time a component publishes telemetry or publishes an event indicating that state changes, or a component talks to another components, any command, all that goes into the EFD. And if you ever did analysis on the data telemetry from the telescope, you interacted with the EFD, the Engineering Facility Database. The components on the system, the software components, are called CSCs. They are commandable SAL components, and the S there, SAL, is the service abstraction layer. So that this is how we abstract the components themselves. So when you have a system that controlling the telescope, controlling the dome, that's a CSC. They expose to the observers a common interface. So if you need to put a component in a state where it can control the hardware, or even if the software component, they all behave the same way. And once they are ready to operate, they have their own specialized behavior. So the telescope can move the telescope component can move the telescope, the dome can move the dome, but they all behave the same when they are bringing up to a operational state. The scheduler is a special CSC. It's the one that will calculate what needs to be observed and when, and then it tells the observatory what to do. So it's the scheduler itself, it's kind of split in two pieces. There's the CSC part that has all the business logic, and then there is the algorithm part that Peter is going to talk about later, that calculates what is going to be observed next. So the CSC is the one driving the survey by using the software that the survey strategy team provides. Another very common component that we talk about is LOV. It's the LSST observing visualization environment. It's basically the UI of the system. That's how the observers interact with the system to operate it, right? So this is the UI for the system. Call it LOV. We also have the calibration system. Oxtel it's a telescope on its own, but it's also part of the calibration system. And in addition to Oxtel, we have in-dome calibration system. Oxtel itself has an in-dome calibration system, and the Simony telescope has its own in-dome calibration system. So all that is part of the calibration system. Just keep in mind, Oxtel itself is its own telescope, right? Part of the calibration system. And well, I already mentioned the coding plant. It's the thing that will put the coding on the mirrors. Here's a little bit of I'm sorry. So the design of the optics. So the mirror system will have the primary and tertiary in one surrogate. The external part of the M1 and 3 is the primary one, and internally has the tertiary. So the primary sends the light to the M2 mirror at the top. It sends it back to the internal part and then back to the camera. It's a really compact optics. You see in the center, we have like a hole here in M1 and 3. And this is where we have a laser tracker. So we can use the laser tracker to do initial alignment of the optics. We haven't been using that a lot, but we tested and it does its work. But we've seen that it's easier for us to just go on Sky and set up the optics with a previously known good location for the optics. That's enough for us to do the initial alignment. And then we don't have to be powering on and off the laser at night. So we have other uses for the laser tracker, but for now, this is how we are using it. The active optics system, we have the 4 components, M1 and 3, M2, the camera, and M2 hexapods. Each one of those individual components have their own lookup table. So it's basically the open loop optics. So when we point a telescope somewhere, they calculate their position or which figure they have to apply on each of the mirrors. Let's see, the calibration system. We use the calibration system, the in-dome and Oxtel, to measure throughput and understand systematics. And I'm running out of time, so I'm gonna skip this. This is a picture when the telescope was first assembled. We didn't have any of the optics components here with this mass simulator for the M2 and M1 and 3 surrogate. And this is the thing with all the glass on it. It's the same picture, but now we have glass and we have the actual components. So on the top, we have M2. The camera is at the center. Here we have LSST cam. The other picture had concam. The TMA, M1, M3 here, you don't see the mirror because it has a skirt around it, and the cell at the bottom. And now we have a calibration screen that was recently installed as well. So I think that's it. Questions? All right, Aaron?
Okay, our next speaker is Aaron. We'll talk about about the camera.
Okay. So this slide has a blow up of all the camera components, ranging from the focal plane, which is kind of in the center inside the cryostat. The focal plane has 21 science rafts. So that's one piece of jargon, a science raft. Each has 9 CCDs. Then there are the 4 corner rafts, next jargon, that have 2 guide sensors and 1 split wavefront sensor. The electronics is in vacuum. We're capable of 2-second readout. You'll see we're actually using 3. There, you heard about the optical system. The camera has 3 lenses. The front 2 are in the front pancake, L1, L2, and the third is the vacuum window. There are 6 filters, but only 5 in the camera at any one time. The other piece of jargon you might hear people refer to are the cold or cryo systems. Those are the 2 refrigeration systems. Cryo cools the CCDs to -100°C. Some pictures. These are from the construction phase. I show them still because otherwise you can't see the guts of the camera since everything is closed up. That's the cryostat on the top left being installed in the camera body. You can see the shutter being put into place right in front of the cryostat. The L1, L2 lenses next, the filter loader, and there are the filters. I have 2 movies showing the shutter actuation and the filter exchange. I'm not gonna show them, they're too long. I'll show one of them. Okay, all right. So I'll show one. The actually, if you're in the control room, both of these actuations make a nice sound. There's a microphone in the camera body, so people observing get to hear the shutter opening and closing every 30 seconds, and then hear the filter systems whir. Those are reassuring sounds. Okay, I'm sorry, I'm just going to go. This one's too long. Okay, this is very early. There's actually no, it's a blank filter being installed. You can see that on the mountain notes. You have to be standing in just the right spot to do it. Okay, a lot of what you as people using the Rubin data will be focused on, of course, are the output from the sensor. So maybe a little bit of detail on the focal plane is warranted. This is a photograph of the focal plane showing the different colors of the sensors in reflection. If you want to know why they have the colors they do, you can ask me, I could tell you all about it. The light blue are ITL, STA 3800s. The darker blue are E2V CCD 250s. One of the science rafts and the corner raft are outlined. There's 16 channel CCDs. For most things, you should not be able to see the amp boundaries. If you do, that means the ISR is not quite tuned up. If you want to know about numbering, we actually do have a document now. CTN, so Camera Technical Note 1, has the map and all of the detector numbering, name, and amplifier name details. So there are 2 different systems. There's a name and a number. Usually online or in the Butler, we'll just use the number. The pictures show the details, the science raft with electronics, the individual CCDs, and we worked very hard all across the project to minimize the uninstrumented regions. So you can see the gaps are truly tiny between the sensors. Okay, just a few more photographs. These were all from this spring of installation. Top left shows the camera getting installed through M2. I think that's Brian Stalder gazing at the camera longingly as it comes into place. Next is the lens cap removal. We do call it a lens cap, even though it's 1.6 meters across. Next in the middle is a filter being installed with a crew. You see all adequately garbed and tethered on the platforms. There's our documentary filmmaker in the bottom that you can see in reflection. And then on the right is a picture of everything installed. And if you can figure out which reflection you're seeing here, you should get a prize. It's actually kind of complicated, but you can see, let's see, since that's reflecting blue, it must be the R filter that you can see there. Do I have time for one last slide? Okay, so operational status. The camera is operating nominally. It is actually performing extremely well. We are still using calibrations that we took in the lab for various parts of the instrument signature removal. Those should be replaced soon, but they aren't quite yet. So it's really performing in almost exactly the same way as it did during our extensive lab testings before we installed the camera. There are some issues, of course. You might have heard that there's one CCD that's not powered on. If you want the details about where it is, just look at the New York Times. It has that information for you. There's an issue that we're in the process of mitigating in the cryo refrigeration system. And there was an issue with one G-band filter exchange last week, and we're actually pulling that filter out. We need to do some inspection. So that's hot off the presses. I'm sure we'll be able to return that filter to use hopefully soon. Just one other kind of detail, we are still, although maybe we're done, maybe not quite done, optimizing the camera performance. And one last piece of performance that we've been able to achieve is that we are probably in the survey going to use single 30-second snaps instead of two 15-second snaps. And as a result, we'll take advantage of some of that time, which is otherwise not used because you're slewing, to slow down the readout just a little. And that gives us a nice improvement in a couple parameters such as read noise. And just to show one piece of our very extensive telemetry, these are plots of just 3 different CCDs temperature over a 2-week period. And you can see that they are rock solid. So maybe I'll stop there and take any questions.
Questions about camera? If not, thank you. And the next speaker is,
Short question about the filters. You have 5 in the filter rotator. What happens to the 6th filter?
So the filter exchange system only holds 5. You have to look at other engineering diagrams to see where we store them. They're stored aft of the outside in radius of the cryostat. So the normal operating procedure is twice a month to swap one out and put one in, usually alternating U and Y. And so those are only used for part of the month, so you don't really lose too much by having only 5 installed at any time. Yeah. They don't fit. They're 80 centimeters across, and right there, you know, the storage location and the way they're installed is extremely complicated mechanically, and there literally is not room for them inside the envelope of the camera body. We would have needed.
To make it from 6,000 pounds to 10,000 pounds.
So this is Lynn Sepala, who co-designed the Rubin optical system. So yeah, having the camera in what looks like the prime focus position meant that you had to obey a certain stay clear, right? The camera is fitted inside the M2 hole, and there's just no more room. Yes, if you want, you can catch me at a break, and I can describe the other constraints that the camera had to fit in that space. They were considerable.
okay, thank you. If you have any further questions, please post them on Slack. And for the in-person participant, please speak into the room microphone so people online can hear you. And Peter, floor is yours.
All right. Hi, everybody. So I'm here to talk about survey strategy. Here's a map in a slightly different projection than usual of our survey footprint. So we've got the South Celestial Pole at the center here. So the terms we're covering, we've got our baseline survey strategy, which is kind of designed to meet the basic requirements and achieve the core science, and then do all the extra science that people think up. And it's our requirements document is the SRD, and so that's what we're trying to meet. One of the terms we use a lot is wide, fast, deep, or the WFD. And so that's the blue area, and the green areas here are the wide, fast, deep. And that's defined in the SRD, usually comes up as this 18,000 square degree area that we need to cover, and to visit it, about 800 times overall filters over 10 years. So then we've got our cadence. So we visit spots approximately every 3 days when they're in season. And our baseline plan is we tend to take observations in pairs. We'll kind of pick a nice blob on the sky, raster it for 33 minutes, switch filters, repeat that raster so that we get colors and can see moving objects, pick those out. More jargon are the DDFs, the deep drilling fields. They're marked here in red. We have 5 of them, and this one is a double field to overlap with Euclid. And then Cosmos is off here on its own, so that one goes a lot deeper than the others just because it's not competing with time at the same right ascension as everything else. Then we have our mini surveys, which are kind of the South Celestial Pole, the North Ecliptic Spur, Magellanic Clouds, and kind of the Dusty Plain. Because there's so much extinction, we've turned down how much we observe on that area compared to wide, fast, deep. But yeah, there's lots of our survey strategy jargon. Oh, and we have our very own website, surveystrategy.lsst.io, so you can get all the details on our survey strategy. More terminology. We have OPSIM runs. This is legacy terminology. OPSIM stands for Operations Simulator. So this is where we have a model of the telescope in the computer and our scheduler brain, and we just run them and say, if the telescope performs as expected, what would a 10-year survey look like? And this generates a SQLite database with about 2 million visits with all the details of those visits, RA deck filter, sky brightness, expected depth, and so on. So you can say, oh, given our strategy, here's what the survey could look like. And we publish those, try to get feedback from people so you can say, yes, this is good for our science, or no, this strategy will destroy our science. We don't get that too often, but every now and then. For the most part, we are going to do very good science. We have MAF, which stands for the Metric Analysis Framework. And so this is kind of the tool we built to take these OPSIM runs, and so that you can easily say, how well can you do science? And here's an example of a MAF output where we're computing the uncertainty of the proper motion of a 20.5 magnitude star. And so as we change the survey strategy, we can see how well we change on our astrometry precision. And you can see, different, again, those 5 deep drilling fields jump out because we observe them much more. We get much better proper motions on those areas. Things like that. The SCOC is the Survey Cadence Optimization Committee. So that's a committee with members from all the science collaborations, and they're kind of guiding the formation of this survey strategy. And my job is to take their recommendations and turn it into software. So that's what we're doing. The FBS is what Tiago referred to as the scheduler brain. So we're calling it the feature-based scheduler. That's because this is an algorithm that's based on a Markov decision process. And kind of the base level of a Markov decision process are features. And so in this framework, everything's a feature. The current pointing of the telescope is a feature. The survey history is a feature. The sky brightness is a feature. So you take all these features, wrap them up, and the algorithm takes all those features and say, okay, here's a good place on the sky to point at this time. Scheduler is a bit of a misnomer. Scheduler implies we do some global optimization. This is really more of an AI. It's doing a real-time decision-making process to say, okay, where do I think is good to point right now? And I don't care what the sky's gonna look like 2 years from now. I wanna know right now. So we are not globally optimized, but I always say for AI, the goal is to not do anything obviously wrong. And so that's really what we're striving for. So we don't want to be changing filters constantly, be pointing sideways. So it's hard to find where we do things obviously wrong, but if you look really hard, you might be able to optimize it more. Okay, and finally, we have SketchView. Here's some example of SketchView, and this is the software package we're making to visualize how the survey is performing as far as pointing on the sky, and what areas we've covered things like that. And so we've got, night summaries and summaries for the survey as a whole as it's going. Some more jargon. One of the things we talk about a lot is rolling cadence, where over here we've got the number of visits over the sky after 1 year. We try to get a nice uniform survey after 1 year because we want to build image differencing templates. But then we start, after 2 years, things get messy because we're rolling. We're going high cadence on some regions of the sky, low cadence on other regions of the sky. So this basically means you'll get much better light curves on some areas of the sky, terrible. And then the next year we reverse, fill it back in. So by year 4, we're back to uniform. And so up here I've got color coded by what filter is in and the dates for one single spot on the sky. So we have kind of a very high cadence season, a low cadence season, high cadence season, regular season, low cadence season, and on and on. So you'll get some observing seasons have great light curves, some not. And then hopefully after 10 years, we end up fairly uniform. And then finally, here's kind of the deep drilling fields, what they look like. Again, Cosmos, we're going to go very, very deep, very high cadence early so that the Cosmos field will be able to check and make sure we can co-add to full 10-year depth on the other deep drilling fields, so we can change the strategy if we need to. And then, this is kind of the last bit of the survey strategy that's under a lot of debate. So if you want to change the deep drilling fields, we are actively fiddling this around to decide, should we do kind of an hour-long drill on a deep drilling field, or should we break that up over multiple nights and do kind of 10 to 20-minute observations several nights in a row? And should we do all filters in a night, or should we split those filters onto different nights? So we're actively working on that. And just here's an org chart. Basically, we've got the survey scheduling team. We talk to the survey cadence optimization committee. They talk to the community. They get feedback. They give their recommendations. We make simulations. We compare how those simulations do for science, and I don't know, it all circles around in a big mess. And hopefully we come up with, we don't even have the final FBS algorithm on here. That's kind of silly. Hopefully this all ends up in that. All right, thanks. Yeah, a question.
What are some of the considerations, particularly about cloudiness or conditions where you just say, we're not going to observe? This is not worth taking data.
Right. So if it's totally terrible, we're going to leave that decision up to a human on the dome.
Of course, but
Yeah.
give me an example of actual limits that go into it, quantitative.
So one of the things we try to do, we try not to,
everything, just rough ideas of kinds of quantitative limits that go in.
Sure. Some of the limits we have on the scheduler, we have a zenith exclusion zone. We can't point towards zenith, so that's a hard mask. We have the moon, so we're refining, a 30
Tell me about clouds in the atmosphere, the variable.
So for the clouds, we have the DREAM all sky camera system right now is returning kind of an extinction map of the sky as we see right now. And so that gets fed into the scheduler. One of the things the scheduler considers is, depth, 5 sigma limiting depth we can get to compared to what it would be in ideal conditions. And so we fold in the clouds, and kind of the scheduler, instead of trying to maximize signal, it tries to minimize signal loss. It says,
and what's the point where you quit? I keep asking for a number.
I don't know. It's when data coming in looks like garbage.
What constitutes garbage?
I don't know. We don't know yet. Probably around 2 magnitudes would be my guess. That's where I'd close. Yeah.
Do you have enough information from Starlink to avoid the Starlink constellations?
Is Tony? Right. So we've run simulations where if you put a 30,000 satellite constellation in orbit, they're currently at around 10,000 or so. So even if you do a full Starlink constellation, if you don't do any attempt to dodge it, we would lose 0.04% of our science pixels. And so we did a simulation where we said, okay, let's try to dodge them. We can cut that number in half, and that would result in a 0.1 magnitude loss in depth. Basically, going to less desirable parts of the sky and spending more time slewing is way more destructive than just masking the streaks. So even if Starlink and all these other things do these giant constellations, the other thing to keep in mind, these are low Earth orbit satellites, so they go into shadow fairly early. So it's, you get streaks in twilight time, and it's 0.04%. So we do have ways we can dodge them, but I really don't want to bother.
All right, let's thank Peter again. Our next speaker is Irfan, will tell us about data management.
Sorry, I thought the mic off. So we are data management. Does it work? Okay. A multi-institutional enthusiastic team of scientists, researchers, and engineers. And we are tasked with building the LSSD science pipelines and the Rubin science platform. LSSD science pipelines performs image reduction, analysis, and all sorts of things that comes with it, which we are going to talk about in the upcoming slides. And all the code we write is open source, installed on the Rubin Science platform. And the code exists on GitHub, available to you. And the idea is we provide science-ready data products in a Rubin Science platform so that you, as an end user, do not have to process the data from scratch. You can go to Rubin Science platform and take advantage of all sorts of science-ready data products that we have there for you. So as the data comes in from the telescope, it gets processed, gets sent up to the US data facility, USDF, and it gets piped around the world. And the interesting thing is that all of that for the first kind of prompt processing happens in just 60 seconds, which is very impressive. So I mentioned the prompt data products, prompt processing, which is one of the three flavors of data that we have. As you see, the first flavor is obviously the raw data we get from the telescope, and then prompt data products, and then data release data products. For prompt data products, there is another time scale other than the 60 seconds or seconds to a minute scale. The other scale is 24 hours, or that we release our data in prompt processing. And the longer data release that we have is data release data products, which happens on an annual cadence. We actually it is being we actually do some study, and we might make some changes to the schedule that we release the data, but it's just an estimation for now. Then I was going to mention the Rubin Science platform, that we have a screenshot of it here. You can go there and start playing with the data that we mentioned. We have a bunch of acronyms here, which I'm not going to go through them because this is a short talk, but you can see them on the slides. So in order to get the data products we talked about, we have to do some processing. So we do prompt processing to get prompt data products, and we do data release processing to get data release data products. A central aspect of prompt processing is DIA, the difference image analysis, or DIA. And here we are showing you a cartoon image of how it is being done. So you have in these three images that you see on the very left. In the first one, you get some template image that later on you get another image, and you want to compare these two images to see what happens in between the two images, like what changed. So in order to understand what happened in between these two times, your naked eyes are not capable of spotting spotting and catching all of the changes that you see here. So you have, even if your naked eye could do it, you want to do it in a systematic way, right? So that's why we subtract fluxes and counts of the images, and we get the image on the very far right. And the goal is to understand what that, for example, in this case, there is a little object at the very center of the image on the far right. So we want to know what it is. So we do it through studying DIA source and DIA object that you see here. And we get all sorts of data products from these analyses. So for data release processing, after we get a 30-second exposure, we don't just store it, so we do some analysis on it. The one that we get at the very beginning is our standard visit. The visit that we get is standard visit that we get at the very beginning. It goes through some calibration, gets processed further to get calyx, and those calyx they can get stacked on top of each other to improve the signal to noise, and we get a coat for it, or a co-added image. And if you want to store all these images across the survey area, and you want to open it in your computer probably would crash. So in order to avoid this, we split the data into smaller regions called tracks and patches, so that you can handle it using a computer. And we have all sorts of data catalogs. We have so-called source catalogs. So for the standard visit, a 30-second image that I mentioned, you want to know where they are in the sky. So you can have a table in order to, which is called source table, and then an analog for that. For a coad is called object table, and we also have 4 source tables, which are some measurements that are on some force position in the sky, which are very interesting to some of astronomers. It's very helpful. So it's my last slide. So if you want to find out more, you can take a look at our LSST-like data products, DP0, or real data that we have. The LST data products that we have is DP0, but also we have DP1, which is based on LSST ComCam. It is real data, and they're both available on RSP, Rubin Science Platform. And you can see a screenshot of it here on the very right. And we have a community forum that you're encouraged to ask questions there. Plus, be ready for data preview 2, which is based on LSST CAM, which is very exciting. And later this week on Wednesday, 1:30 p.m. to 3 p.m., we're going to give you an update on what we've been doing in DM to improve things. So I invite you to join that on Wednesday, 1:30 p.m. That's it.
One quick question, if there's.
Thank you so much. This was a great talk. I was kind of curious about DP1. I know I was playing around with it and I was trying to see if there were co-added images. Yes. And I don't know if they didn't exist at the time or if they're coming soon. I was kind of curious if you could speak more to that, and if they don't exist, are there tools available for us to do it ourselves?
They do exist. So last I checked, they existed on RSP. So maybe at that time something wasn't working, but I'm pretty sure that they checked and they exist.
Okay, got it.
Yeah.
All right, thank you, Irfan. If there's any other questions for the data management, please go to the Wednesday session.
Yes.
Right. Okay, so our next speaker is Frosty, who will tell us about the Rubin Science Platform.
Hello. How many people have used the Rubin Science Platform already? Excellent. The rest of you, what are you waiting for? Okay. Right, I'm going to try to catch us up a little bit because we're running behind schedule. The Rubin Science Platform is, of course, a data management activity, as Erfan just said, but it's very user-facing. So we're going to talk to you a little bit about it, but there's much more tomorrow. So I'm going to try and catch up. So currently, the Rubin Science Platform preview, everything is in preview, the data is in preview, the software is in preview, is a data cloud, which is our user-facing science platform, has 3 data sets. Data preview 1, based on the ComCam data preview 0.3, which is simulated solar objects, and DP 0.2, which is the simulated desk data. The simulated ones will eventually roll off as we have more real data. And as Erfan said, DP2 is going to be full LSST-CAM data. Just want to say that we are planning on developing the Rubin Science Platform until they hit the breaker, switch off our lights, and kick us out the building. So it's not a case of whatever is available at the end of DP2 or even DR1 is the full feature set. We are watching what people are doing. We are always looking to see what we provide. And throughout the duration of the survey, we're going to keep rolling out more capabilities and more features. As people who use the science platform probably realized there's a lot kind of going behind the scenes. All the services that you use, the data assisted cloud, are running on Google Cloud, and for both availability and scalability. Some data is stored on Google Cloud, but eventually gets expensive, at which point data is also stored at Slack. But you don't know this because as long as the services are working, because the services go fetch the catalogs or images for you from wherever they are. And yes, we do have coads for DP1. Okay, so things to know. Number 1, if you are a user of the Rubin Science Platform, come in tomorrow's session. You will be bored by the presentation, but you'll have a chance to ask a Q&A. It's going to be very informal. Number 2, if you're not a user of the Science Platform, come to the session tomorrow. You will not understand the Q&A, but you might learn something from the presentation. So something for everybody. There's a whole bunch of links about things, how to get guidance. We have the actual Science Platform documentation. We have dp1.lsst.io, which is a description of the products and how to find them and access them. There's the forum where there are these 2 sections that you might want to look at, particularly the news. Every time there's a new feature, we post it in the data services part of the news. And there's also the support category for Science Platform questions. If you use data.lsst.cloud, sometimes there's a giant banner in your face when you go to the home page. Do read it. It's probably important. I realized that after a while, he kind of stopped reading banners, but that also has news and also any service interruption information. And come to the session tomorrow, and we should just roll off and talk about communications. Questions? Excellent.
Thank you, Frosty. So our next speaker is Kristen Metzger, will tell us about the communications.
Hi, everybody. So my name is Kristen Metzger, and I work in communications and education and public outreach, which at Rubin are not quite the same thing. And I inherited this talk a few years ago from Ranpal Gill, whose name I'm sure many of you have seen if you haven't met her in person. She is the communications manager for construction, Rubin Construction. As you know, construction is about to officially end and segue into Rubin operations. So a lot of the structures of how communication works for Rubin are about to change. And I don't know exactly how yet. We're hard at work building new structures and new processes and new workflows. So I'm going to tell you about some things that are staying the same. And then at the end, I'm going to tell you what to do about the fact that everything is probably about to change. So first, we'll talk a little bit about our name. As you probably know, we are Rubin Observatory, but our full name is NSF DOE Vera C. Rubin Observatory. We're jointly funded by the National Science Foundation and the Department of Energy. And so when you're using the Rubin name, we do ask that if you can, if you're putting out something that's going to be read widely, that you help us out by following our branding guidelines, which our agencies really like us to remind people about. But Rubin will be conducting the legacy survey of space and time using the Simone survey telescope and the LSST camera. If you forget how and when to use all the different versions of our name, there's a handy name guidelines. The link is in this slide. And you can also get that from the project website. So the one thing we ask, if you remember nothing else, is to please not use the acronym VRO. I know that many people in this room love acronyms, and that's great, but we want to honor Vera Rubin, and it's a lot easier to do that when we use her name as opposed to an acronym. So we try to catch that whenever we can. It still happens. Sometimes articles about Rubin use that acronym, but we're asking you to help us sort of spread the word that we prefer. If you're going to shorten it to Rubin Observatory instead. Okay, so you heard a lot of acronyms and jargon, and you probably didn't write it all down. I hope you didn't. I'm going to give you the decoder ring for all that stuff. There's actually a glossary that can be found from the project website. And it has all of these acronyms that you've been hearing. You can enter something and find out what people are talking about. So if you can't remember what the SAL is, you can go in there and look it up and find out that it is the service abstraction layer. And then you might say, what is that? And that's a whole other thing. There's also this really cool hack on the LSSTDA Slack space, the big community Slack space. There's a glossary bot. And so if you type in glossary, you can get your words or your acronyms that way too. So very handy little hacks for you. So we, in operations, Rubin Observatory has one website. It is rubinobservatory.org. I am told that our project website, which is project.lsst.org, is sticking around. So that is probably going to happen. But we have migrated all of the information for the science community to rubinobservatory.org. So it is a great place to start from if you're looking for anything related to Rubin. There's a tab called For Scientists, and you'll see that there's all kinds of resources there. So when in doubt, go to rubinobservatory.org and go to the For Scientists section, and you should be able to find what you need. We also have other places that you can go to find out what's going on with Rubin. We have very active social media accounts, thanks to Steph Deppa, who's hiding in the middle of this audience. We've got lots going on our social media, and I encourage you to follow Rubin on any platforms that you're on. You're going to learn about a lot of the things that are going on, both things that we want to communicate to the public and also things that are a little bit more internal and of interest to the science community. Also, of course, you've heard about the Rubin Community Forum. I highly recommend that you get an account there, and that's where all the science discussion is going to be going on. We also post announcements and things in that space, and we'll do that increasingly as we're in operation. So that's a great place to get news and updates as well. Okay, so here's the stuff that's all changing. So this photo is of our communications team as it existed during construction. Pretty much everybody in that photo is still going to be working in some capacity with communications in operations. So we do have an email address right now that is communications-team@list.lsst.org. And I think that's going away. It still exists right now. You can email us anytime with your questions. But I guess what I would say going forward is that if you have questions about how communications is working in operations, you should just Slack me, and I'll tell you what I know at that moment. So feel free to reach out to any of us. We are always available to answer your questions and to help you with anything you want to communicate out or to find information that you need from the project. And that's all I've got.
Questions for Christine? If not, let's move on to the next talk by Claire Hicks. Tell us about education and public outreach.
Hello, so my name is Claire. I'm the astronomer on Rubin's education and public outreach team. I want to give you a brief look at who we are, what we do, and how we do it. And so starting off with our mission that's up here in teal, what we try and do is create online data-driven experiences that are accessible, approachable, adding real-world context and opportunities for people to engage with Rubin. And so as we know, and as we have heard in this session, Rubin is complicated, technical, fascinating, and complex. And what we really try and do is create ways for the public and the world and everyone to enjoy and appreciate Rubin. And so our team, the EPO team, serves non-specialist audiences who are interested in Rubin. However, I hope that many of the things we do are interesting to specialist audiences, such as yourself as well. And so I think it's important that everyone in the Rubin community know what we have, because there are many things that hopefully can be useful to you in many ways. This is a photo of our team taken January 2024, so it's slightly out of date. And so we have it's missing some new of our team members. There's actually multiple EPO people in the room right now, and so I'm going to ask you to wave. So we have Alan, Fernanda, Sasha, Steph, Kristen, and I think I saw Eric earlier. Yes, Eric is still there. Okay, so there's lots of EPO people at this meeting, and so I hope you chat to us if you'd like to. So what we try and do what we do to try and achieve this goal, we have a whole bunch of stuff. Going to touch on a bunch of things that might be of interest, and there's much more. Of course, the website Chris just mentioned, it's our public facing website. We're really excited to put all the first look images and show them in all their glory there. But there's lots of stuff there for the public that's also interesting. On the website, there's also a gallery. If you ever need a beautiful image of Rubin or a technical diagram or kind of a fun animation or graphic, check it out there. We also have animated videos that are on our YouTube channel. I point these out because they're nice little videos, but they often have great little graphics and things that are great explainers. We try and do everything for the public, so we try and keep it nice and simple and clear. So they're all there. We have a formal education program, which I'll touch on in more details in the next slide. I do want to point out this resource portal, which is ls.st/resources. That's where you can find many of the things that I have mentioned, and feel free to use it. One of the new additions is really handy, is a grab and go slide deck for outreach. So this is kind of Rubin 101 for the public. It's for the community, it's for you. It's in English and Spanish, and it's fully editable. So the idea is you can grab it, you can take what you want out of it and leave what you don't, and add whatever you need. Of course, social media, and we have data visualization for the public, which is also fun for everybody. Just touching on our formal education. So the idea here is bringing Rubin data into classrooms. So we have these formal education modules. They're kind of geared to 8th grade through 1st year university, so Astro 101 style courses, covering a range of topics. Those are the ones that are currently live, and they're currently live with real data, but not Rubin data. And we're excited to transition these to Rubin data now that we can, which is very exciting. But these are great because they're browser-based, and so it's bringing Rubin data into the classroom without having to download anything or install anything, and lots of fun widgets and graphics there. Our data visualization apps that we have here, released earlier this year. These are our ways for showing the public what Rubin data looks like. The Rubin Science Platform is great, of course, for our science community, but if you just want to look at some pretty pictures and explore, it's more than you need. So we have these two sister applications. We have Sky Viewer and Orbit Viewer. Sky Viewer is an all sky visualizer, whereas Orbit Viewer is focused on the solar system. A Sky Viewer is currently showing the beautiful first look image, the cosmic treasure chest of Virgo, and has a sonification layer in there too, which if you haven't discovered, I highly encourage. One of my favorite parts. But then Orbit Viewer is the same idea, but it's showing discoveries in our solar system, and you can filter it for just Rubin discoveries. And so both of these are going to grow, obviously, with Rubin. And I would say, of course, they're for the public, but they are a great way of just having an overview of what's there. Final thing I'm going to mention is citizen science. So one of the parts that the EPO team is supporting is helping scientists in our community create great citizen science projects for the public. So we partner with the Zooniverse. And so our team is not running projects, but we're helping scientists run projects and trying to create a community of engaged volunteers who are super excited to embark on this 10-year plus marathon of science that's about to happen. And so making sure we have volunteers who are ready to come for it. And our first project is live, which is Rubin Comet Catchers. Very exciting. So that's just a brief overview of some of the main parts of our program and who we are. If you want to hear more about EPO at RCW this afternoon, we have a citizen science and outreach resources session. The first look show and tell on Wednesday afternoon, I know has some EPO related stuff. You can of course use social media on the website or check out that ls.st/resources link. But most importantly, there's many of us here at RCW and we're all on Slack and we are always happy to chat about any ideas, whether we have something that would fit whatever you're thinking or yeah, if you have any creative ideas, we're always happy to chat.
All right, any questions for Claire? All right, if not, thanks. And our next speaker is
I'm in all of them, and so I can point you in the right direction.
Right, thank you. Our last speaker is Beth Willman. Will tell us about link frameworks.
Thanks, Alex. I'm actually going to tell you about LSST Discovery Alliance.
Sorry about that.
One of our programs is link frameworks, and I'm not giving a summary, but my name is Beth Willman. So we heard a lot about the Rubin project itself, all of the different pillars and subsystems, what's going to deliver this just incredible revolutionary data set. We just heard from Alex about the science collaborations, a second independent pillar from the Rubin project. Right, the Rubin project is funded by National Science Foundation and DOE, independently organized, thriving science collaborations around the globe. LSST Discovery Alliance is the third pillar of the Rubin project, the Rubin Observatory ecosystem. And so our role, and why the heck is there a table out there? If anybody's wondering, what is this LSST Discovery Alliance table? Our role is to position the global community to get the most possible discovery out of Rubin's LSST. And we've heard how this is in science as usual, and there's many different new types of resources, tools, training, and networks that are needed to maximize this science. So you'll hear a lot of parallels in what we're doing from what you've already heard, and we work very closely with the project team and with the science collaborations, with formal input channels from the science collaborations to ensure that what we're doing is what the community actually needs and complements what the project is doing. And so the Discovery Alliance has actually been in existence for more than 20 years. We incorporated in 2003 in Tucson, Arizona, to start what was then known as the Large Synoptic Survey Telescope, with the idea we design, develop, construct and operate the thing. A $1 billion federally funded observatory isn't necessarily best managed and deployed by an alliance of dozens of university and research institutions around the world. So over time, roles changed, and now we're focused on maximizing that science. And I'm going to tell you a bit about what specifically it is we do and how we do it. And many of the programs that I'll be presenting are available to scientists at non-member institutions, not at these 40, but some of them are only available to member institutions or have preferential opportunity for folks at member institutions. And so our approach, and this parallels some of what you just heard from Alex in terms of what the focus areas of science collaborations are. In order, as we strive to try to ensure that any scientist with a great question to pose of the LSST data set has access to the resources needed to answer it, we think about this in terms of, three pillars. The cutting edge, technical and software tools and resources needed to manage this once in a lifetime data set. The training and skill building that many members of the community from early career all the way up to senior scientists are asking for so that they can learn how to apply their science and apply their questions to this new type of data set. And then the networks for global collaboration and professional development at all levels. And again, we just heard from Alex, This is why we need these large, diverse collaborations to tackle this new type of data set. And so, thinking first about these 3 different project areas, I'm just going to highlight this up here. I'll talk about this again briefly tomorrow morning at the plenary. And at the end of this talk, there's a QR code to our website if you're interested in learning more about any of our programs, where we have tools, training, and collaborative networks. Some of our programs are ongoing, right? We're a privately funded nonprofit. We get funds from individual philanthropists, foundations, and member institutions. And so we're always out there trying to figure out what's giving the most community science community impact, and then seeking refreshed funding for it or seeking launch funding. And so you're going to hear about Link Frameworks here. There's a hack days going on, incredible project. There's going to be a software session on Wednesday. We'll hear a lot about that. You're also going to hear about Project Dovetail. We've got training programs that are ongoing. I'll say a few about the undergraduate. There's a number of undergraduates in the room right now who are part of our summer student program, and graduate student and postdoctoral program, as well as a set of ongoing resources to help bring people together. So some of these programs, their short-term goal is discovery that wouldn't have otherwise happened. Others, it's more of a long-term goal, getting people in the room, giving them that training, giving them the professional development to launch them on a path to success. And so I don't want you to think that we're in silos here, right? The tools, the training, collaborative networks. One of our core characteristics is the interconnection between all that we do. And again, I think you heard a bit of that from Alex in terms of the science collaboration strategy. And so I'll highlight 3 flagship programs that are funded and thriving right now: the Catalyst Fellowship, and now a Catalyst Postdoc Alliance. I know some people here have recently applied to be part of that if you're a postdoc at a member institution. The Link Frameworks, again, funded by Schmidt Sciences, with lead investigators at Carnegie Mellon. We've got Rachel Mandelbaum and Jeremy Kubica at University of Washington, Andy Connolly, and their really extraordinary teams of research scientists and engineers are building analysis software that's scalable and open for Rubin data. And then they work with folks like Frosty to get it integrated into the Rubin Science platform, or feel like see how these things can play nicely together, right? And then the Data Science Fellowship Program is the first flagship program that was launched through what was then LSST Corporation, and it's for graduate students. And just last year, we had a week meeting where we brought together individuals from all 3 of these projects who are engaging in different hacking and collaborative work together, building cohorts and networks across these boundaries. So another aspect of our approach, right, tools, training, networks, interconnecting our programs, is that the scientific community programs, to maximize the impact, right? We've listened to the community over a long time. Our programs are all very person focused. They're all very scientist focused. And so it's not that we're throwing resources under the wall. We're not throwing stipends over the wall to undergrads so that they can come to this meeting. We're inviting them here. We're giving professional development. We're having the students cohort build together. The Link Frameworks team isn't throwing software over the wall, posting it on GitHub and saying, have at it. You're bringing the community together to get the input on what needs to be built, building it, and then iteratively interacting with the community to ensure that the things that are getting built remain a fit to the science community's needs. Again, you heard the same thing from Frosty on their approach to how the Rubin Science platform is managed. And again, I don't want to put this lightly. This is a huge amount of effort, and we're seeing this community-centered approach from the project to the science collaborations to what we're doing. And it's one of the reasons, as Jelko told us at the plenary, Rubin's LSST will be the most impactful astronomy experiment of all time. And so finally, talk to us. I'm here. I'm the Chief Executive Officer of the Discovery Alliance. The chair of our board, Michael Woodvasey, is here. Amanda is our Director of Strategic Engagement and Philanthropy. She's here. She's in the room. And so is Jenna Sokolowski, our Chief Scientist. We're all here. We'd love to hear from you on what you're interested in, what your questions are. And I bet our website could answer some of your questions. You can go to lsstdiscoveryalliance.org or scan the QR code. And here's just the foundations that are funding our current programs right now. Please stop by our table if you want to talk, have any questions, or you want a pen. Okay, thank you all so much for being here.
who came up with the really new acronym for LSST?
So the Legacy Survey of Space and Time, I don't know if there was anyone in the room. I remember there was a project and community workshop a number of years ago, and we knew that Large Synoptic Survey Telescope was going to go away. And I recall specifically two of the people, and at the risk of, you remember? At the risk of leaving people out, but it sounds like Frosty knows the story better.
Yeah, we have a JIRA ticket proving provenance. So what happened was when we were going to abandon LSST as a telescope name to go to Rubin Observatory in Chalcedony, our worst fear was that somebody was going to make us rename all the Python classes that started as LSST. So data management was incredibly motivated to keep LSST somehow in the mix. And so we threw around acronyms, and my kid was watching a lot of Doctor Who at the time. So like space and time. So I think there were a couple of suggestions: large survey of space and time, legacy survey of space and time, and one of those one. So that's the story. We did not want to rename the code. So
I love that there's a JIRA ticket with your name on it.
Thank you for sharing that story. Any other questions? Okay, if not, let's thank Beth again. Right. I'm really sad that we have to squeeze all this cool informations into like 5 to 10 minute talk. So it's a lot of effort from all the different teams and Rubin Science staffs and LSST, DA, and the science collaborations. So thank you, everyone. So before we go to lunch, I'd like to quickly summarize ways to learn more about Rubin. So first, as Alex mentioned, join science collaborations or many, and you can use the Rubin Observatory Community Forum and ask questions there and get support. And then there are a lot of resources and publications. You can check it out, and including those listed here. And I hope you feeling a little familiar with the Rubin by now, or at least you have some ideas to where to look at for more information. And also feel free to talk to people during the lunches and breaks. The members of the users committee, here's the faces. So I give you a second to stare. And then members of the community science team, including myself. So please come to talk to us. And the last few notes, so especially for the new to Rubin, the people who are new to Rubin, these two sessions are especially useful. So the DP1 session, which is right after the lunch in this room, and then the users committee session on Thursday in the morning. And then the lunch break is one hour and a half long, and it's on your own. So enjoy the lunch and welcome to the workshop. Thank you.